Hello everyone, welcome back to my channel. Today we'll discuss the Davisson-Germer experiment. This is one of the famous and most important experiment in modern physics, which is the direct first experimental evidence of revolutionary famous de Broglie hypothesis. Myself, Dr. dranimaghosh, Associate Professor of Physics, SR University, Warangal, India. The Davisson and Germer experiment is one of most important experiment in modern physics because it provides the very first direct experimental proof that electron exhibit like wave-like behavior. The experiment was conducted in 1927 by Davisson and Germer at Bell Telephone Laboratories. Actually, before this discovery, electrons were generally considered only as particles. However, the French physicist Louis de Broglie proposed the de Broglie hypothesis, which suggests that particles such as, let's say, electrons, it can behave like a wave. The Davisson and Germer experiment verify this hypothesis by demonstrating electron diffraction when a beam of electron scattered by nickel crystals. The observed diffraction was similar to the diffraction of light wave, confirms that the concept of wave particle duality, and this result became a key piece of evidence for the development of quantum mechanics. So thus Davisson-Germer experiment played a crucial and vital role in establishing the wave nature of matter, and it opened up for many modern technologies like electron microscope, semiconductor devices, etc. So very first, since it's related with the de Broglie hypothesis. So what is de Broglie hypothesis? That in de Broglie hypothesis, the wavelength is inversely related to the momentum. So that means the wavelength lambda that is equal to h divided by p. H is the Planck's constant. H is Planck's constant. And P is equal to mv, which is basically the momentum particle. So de Broglie hypothesis says, we can see here that this wavelength lambda that is inversely proportional to momentum. So it says the duality of light means light behaves as wave. Wave means like diffraction, interference. Particles means it shows the photoelectric effect, photons. So this de Broglie hypothesis basically unifying the bridge that it connects the classical and quantum physics, forming the absolute basis for the modern quantum theory. So the Davisson and this Germer experiment is confirmed by observing electron diffraction when electrons are scattered from a nickel crystals. This discovery supported the concept of wave particle duality and became an important foundation for quantum mechanics. So it's first come that wave mechanics inherently exhibit the phenomenon of diffraction, If de Broglie hypothesis is valid, then wave matter must exhibit the diffraction. If so, then the with accepting this concept, the Davisson and Germer designed an experiment to search the diffraction of an electron beam, seeking the direct evidence of wave nature of electron. So from this experiment, the expected outcome is that if electrons are purely particles, so they will bounce off a surface in a pattern of random scattering as shown in this diagram, that the electrons, if they are only the particles, they can scatter in a random way similar to marble sitting on a uneven floor. If we just drop a marble in uneven floor, then what will happen? It will be hit the surface in a very random way and give the random scattering as shown is this diagram. And other way, if electrons act as a wave, then they will interference one another, and it will result in diffraction peak at specific angle. So now let's see that what is the insights of Davisson and Germer experiment, Davisson-Germer apparatus. So at specific and it's a predictable angle similar to X-ray. So now let's see that for what are the main apparatus is used for setting up this Davisson and Germer experiment. That in this, basically here are three important or major part. One is the electron gun. So in electron gun, basically use a low tension battery, and low tension battery here it is this low tension battery. This is basically it heat the low tension battery. It basically heat the filament. And a high tension battery here, a high tension battery we can see here. So high tension battery is basically is accelerate. It accelerate the beam. So it accelerates the beam with a potential difference, and then there is the target that electron beams initially use a low tension filament to heat the filament and produce the electron. And this an accelerating voltage from this high tension battery, it's come through a potential difference, and then incident beams comes in this dotted line and then falls on the target. Here target is the nickel crystal. So this crystal is here, nickel crystal. So here scattered the incident beams which are coming through this line, and then they will be scattered in this angle phi and in this direction, and this scattered beam will be detected by the detector, electron detector. So this detector basically form with a Faraday cylinder connected to a galvanometer, and it capable of moving along a circular graduated scale to measure the different scattered beam. So here if we see that look that in this experiment it is a very simple but very uh, very famous experiment here. It is using the electron gun and accelerating system, and in target it is nickel crystal target, then detector, and then and also using the vacuum chamber. The entire experiment basically conduct in a vacuum to prevent the collision with the air molecule. So basically here that as mentioned that electrons are emit from the heated filament from this part of the electron gun. These electrons are accelerated through known potential difference, and then accelerated electrons strike the nickel crystal surface over here, target, which is the target, and that electrons scattered through this crystal surface, and the scattered beam will detect by the electron detector. So the intensity is record here, and it is capable to record with various angle. So what we are getting from this experiment, or what is the observations, that in isolating the variable to test the diffraction, first generate as accelerate. Electrons are produced by heating a filament, then accelerated via a highly controlled potential difference, then target interaction, and finally variable measurements. So here the key message is the primary beam energy, target angle, and the detector position were all systematically varied. So this beam energy, target angle, and detector position were all systematically varied here. So now mapping the scattered electron intensity. As the Faraday cylinder move on a circular scale, we see that this is the circular scale. For a given accelerating voltage V, it maps the intensity of scattered electron. So here the main observation is that that at low voltage like 40 volt to 48 volt, from here first left to first three images, the scattered curve shows the minor fluctuations. Here we can see that this fluctuation we can see with minor, and but a voltage increases and a distinct peak began to increase. So this part we can see that from 48 to 54 here it is change is more prominent. So and a peak began emerge a specific direction. So here we can see this and seen this with further increase. So, a maximum intensity peak occur when accelerated voltage is about 54, and angle is here, we can see the 50 degree. So, the diffraction pattern match with the Bragg's law. Bragg's law, in one of my YouTube channel, I have added the Bragg's law, so you can see the details of the Bragg's law, which is normally used for X-ray diffraction in crystals. The wavelength calculated from this diffraction pattern match wavelength predicted by the de Broglie equation. So this confirms electron behave as a wave. How? That here we see the critical anomaly at 54 volt, and at 54 volt incident beam, there the diffraction, this scattered angle, this is 50 degree. The diffracted intensity shows striking maxima and minima, proving the electrons were diffracting exactly like the X-ray. So we are proving one by one the hypothesis. And next, the most prominent bumps in the curves occur precisely when the electrons were accelerated by 54-fold. So if we see the number of scattered electrons and the degrees, and with different angle, we can get a curve like that. So at 54, we can see here, this pronounced the scatter diffraction at exactly angle of 50 degree. So now to see the mechanism that nickel atoms nickel, this is the crystalline. So here these are the different planes. We can see crystalline planes act as a physical diffracting grating. So under this specific condition, that means 54 volt and 50° phi, the surface row of nickel atoms perfectly mimic the previously ruled lines of the optical diffraction grating. So if we just draw with this diagram, we can see that, let's see. So this is coming the incident beams and they are scattered in this direction. So this is the 50°, and if we just take in this, so we can get this angle as 65°. And these are the different plane. So interplanar placings are the distance between two planes. So this is two consecutive planes. So this distance is from the Bragg's diffraction pattern. We can find D is equal to 0.091 nanometer. So the atomic spacing of the nickel crystal surface calculated to be 0.091 nanometer or 0.91 angstrom. So the calculating the theoretical matter is that this formula actually lambda is equal to 12.26 divided by root over V, where V is the oscillating voltage. So this is according to de Broglie hypothesis in our previous lecture, how from this formula comes from the de Broglie's wavelength that we have already shown, that we know from de Broglie hypothesis that lambda is equal to h divided by p, and we know that this p that is also equal to h divided by twice me, where e is the kinetic energy, and if this energy is equivalent to the electron charge and the oscillating voltage Ef, then from here we can find for oscillating voltage this lambda with some, if we put all the value of mass, lambda, etc., then we can get from de Broglie wavelength that lambda is equal to 12.26 divided by root V Armstrong. So here we see that this voltage V is equal to 54 volt. So if we use this 54 volt here, we can find out the lambda value. So lambda we can get from here. So lambda we can find out here that in 54 volt at 1.67 angstrom, and we have theoretically calculated wavelength of 1.67, that is perfectly aligned with the wave behavior observed in the 50° diffraction spike. So this value this definitely proving the de Broglie hypothesis. So this proves the Davisson-Germer experiment confirm the wave nature of electron and experimentally verifying the de Broglie hypothesis. So from this experiment, the key conclusion is the electron exhibit diffraction and interference. Matter has wave-like wave-particle duality, and this experiment provides the strong support for the development of quantum mechanics. So this is the provided the first direct experimental evidence for the wave nature of electron. It proved that particles like electron do not always act like tiny balls but can act like waves. So fundamentally motivating this the foundation of quantum mechanics, and This Davisson and Germer received the Nobel Prize in Physics in 1937 for this paradigm shifting this discovery. This wave particle duality, this the realization that matter behaves like a wave is uh, not just like a academic curiosity, but manipulating the ultra short wavelengths of subatomic particle subatomic particles, we have unlocked the imaging and computing capabilities that impossible with classical physics. So with this Davisson-Germer experiment, this we can explore further for the electron microscope that this achieve the ultra high resolution because electrons wavelengths are vastly smaller than the light. So resolution formula for the 0.61 lambda divided by Na. And also you can explore the neutron diffraction that this utilize the wave nature of neutron to analyze deep material structure, and also the it vastly used in quantum computing to directly exploit the quantum wave properties like superposition, interference for next generation computation. So, for this experimental understanding, the some mathematical key concepts or mathematics of wave matter that given here the wavelength in terms of kinetic energy lambda, that is h by root over twice me. Wavelength oscillated with electrons, which we are using here, lambda is equal to h divided by root over twice mev. Since we know the Planck's constant charge and mass of electrons, one easily can find out from here the simplified electron wavelength, that is nothing but the lambda is equal to 12.26 divided by root over root v angstrom. And also the wave velocity and the particle velocity is related with velocity of light with this formula. U is equal to c square divided by v, where c is the velocity of light, and this velocity of v is less than the velocity of light. So we will discuss the phase velocity and wave velocity, phase velocity and wave velocity. Phase velocity or wave velocity of de Broglie wavelength. So phase velocity of a wave is define the velocity with a particle which a point of constant phase such as k star dot moves in space. So mathematically the phase velocity v, or generally write as vp or v, that is equal to omega divided by k. So this omega is the angular frequency. Angular frequency, and this k is a wave number. And this phase velocity of de Broglie wavelength, this is for a particle, it all depends on momentum and energy. So although the phase velocity exceed the speed of light, it does not violate the relativity because the phase velocity does not carry energy or or informations. Only the group velocity represent the actual velocity of particle. So group velocity is actually this Vg is equal to V. The phase velocity is the velocity of wave phase, and for de Broglie wave, that Vp, that is E by E divided by P, and final relation is which is related with the light velocity. So will come that the concept of phase velocity helps to explain the wave nature of particle which predicted by de Broglie hypothesis, while the phase velocity of matter waves can exceed the speed of light. The actual motion of the particle is described by the group velocity, which is always less than or equal to the speed of light and consistent with the special relativity. So now if we draw this relation that a particle of mass m, let us consider a particle of mass m which is moving with a velocity v, has a wave associated with it whose wavelength is given by from de Broglie hypothesis lambda, that is equal to h divided by uh, h divided by m into v, that is the m is momentum. So now let E be the total energy. So let us consider that capital E, total energy of the total energy of the particle, and let small v, that is the sorry nu, this is the frequency of the associated wave. Then we can equate the quantum expression that E is equal to h nu with this relativistic formula that total energy which is also equal to that E also equal to that m c square. So we can get h nu that equal to m c square, or we can write as nu that is equal to mc square divided by h. So now if we use this part, and then we can get the let Vp, that is the de Broglie velocity. Then we can write Vp, that is equal to lambda, that is mc square divided by h into h divided by mb. So we can get it Vp, that is equal to, so but the particle velocity v is always less than c, the velocity of light. Therefore, the de Broglie wave velocity or phase velocity must be greater than C. So today this lecture is up to this. Hope it will helpful for you. If you like the lecture, please click the like button. And if you want to get more updates on my lecture, upcoming video lectures, subscribe my channel. Thank you very much.